Hello guys, this is Rich Raymond, your instructor, talking to you from Mobile, Alabama. This is the recorded lecture that you're required to watch on Thursday night, or you need to come in and look at it a little bit on Thursday if you don't complete it, because I have to call a roll for the class, so you need to log into Blackboard and maybe start the lecture on Thursday night. But as far as when you complete it, that's up to you. You just need to have it completed before the end of the break. What we're doing is we're talking about field effect transistors, which is chapter 11, and we'll start off with a little review of what we talked about in class the other night, and then we will move on from there. But this is a little review. So we need to understand that FETs, field effect transistors, operate completely different than bipolar junction transistors, or BJTs. What we found out in our study on the BJTs is these guys use a base current to control a collector current, which is also basically equal to an emitter current. Of course, we know from what we talked about that the biggest current in the transistor is the emitter current. So the emitter current is actually equal to IC plus IB. But we know that IB is very small, so these guys here are practically equal, but they are not equal. Okay. So the BJT is using the base current to control a collector current or an emitter current. But normally when we talk about it, we said base current over emitter current, because when we calculate the beta, or what we call the H of FE, this is going to be, this is the current gain of the transistor, and it's IC over IB. And we know when we calculate gain, it's always out over in. So what we do is we put a current into the base, and it in turn creates a bigger current in the collector. So what we get out of a bipolar transistor is we get current. So what we do is in this guy is we use a base current to control a collector current or an emitter current. Now all FETs use a voltage to control a current. And what we say here is the FET is going to be using a gate voltage to control a drain current. And what we'll do is later on in a minute, we're going to look at the actual symbols, and we identify the three leads of a FET. So similar to a BJT, an FET has three leads. In fact, just looking at the FETs and the packages that they're in, they're going to look exactly like a BJT. So this is where the partner will come in, and we'll also show you how to check the FET with a ohmmeter. In fact, I think I told y'all in the other class that one of the transistors that I gave you that everybody said was bad because it was not a BJT, it was an FET. So in actuality, the transistor itself was good, but I wanted to give you something that appeared to be bad. So we know that what we do on an FET is we have what we call a channel. And the channel is a connection between the gate and a source. And this is one of the ways, and I'll look at it on the next slide, we identify the channel. So if the channel is made out of N material, then the gate is going to be connected to a P material, and we would refer to this as an N channel FET. Now vice versa, if the channel was made out of a P material, then we would refer to that as a P channel. So similar to BJTs, we have what we call an NPN transistor, and we have what we call a PNP transistor. Well, in FETs, we have what we call an N-channel FET or transistor, and we have what we call a P-channel FET. So that's the big difference. And of course, the illustration that I showed right here, This is the illustration for an N-channel FET, or of course, FET means by a field effect transistor. Okay, but they're still transistors. So the three leads, if we drew this normally, how it's set up, this lead up here right now would be the drain, and then this lead right here coming in would be the source. But physically, it looks just like a bipolar transistor. Now, what we're going to do is we're going to come up here on our P material, and we're going to apply P. So this is P material, and like I said, it encapsulates it and loads it around. What we're going to do is we're going to add a polarity, and we'll start off with a polarity of 0, and we'll show you all that on the next slide. But what we're going to do, and let's go ahead and look at it. What we're going to do is we're going to establish an electrostatic field, a reverse bias field, between the gate and the source. So this is what we're actually looking at when we says it's reverse bias. So an FET is a unijunction device, which means it only has one p-in junction. And we can check this between the drain and the source, and we can check the exact same junction between the gate. Did I say that right? We can check this junction between the gate and the source using our diode scale on our ohm meter. Or we could also check the same junction between the gate and the drain. Okay. The reverse bias voltage between the gate and the source controls the size of the channel, which which controls the drain to source current. And of course, what we do on an FET, what we're talking about, a junction FET. So let's get this correct. So we got several categories of FETs we're going to look at. The two major categories we have is what we call a JFET. And of course, the JFET stands for junction field effect transistor. And then we're going to have something else we call a MOSFET. This stands for metal oxide field effect transistor. This also could have been called an insulated gate field effect transistor, which originally came out with what we call an IGFET. But over time, this has become the predominant means of representing the next section that we'll talk about. But what we're going to do is we're going to start out talking about junction field effect transistors, or what we refer to as JFETs. Now, JFETs actually have a junction. So that's the big difference between a MOSFET and a JFET. A MOSFET does not have a p-in junction that we're going to bias. And we'll look at the structure and how the thing is made up when we get to MOSFETs. But a JFET has a p-in junction. And now what we're going to do is we're going to come up here and we're going to apply some type of polarity between here. Okay. Now what would happen as soon as I did that, we would have current flow, because there's a semiconductor and there's a path through there. So the current would flow through the JFET all the time. So that means if I came over here and took an ohm meter and put it between the drain and the junction, the drain and the source, we're going to get it's going to look like a resistor. It's going to have a resistor value. But what happens is when I come over here and I'm going to use another battery, and we're going to use an N channel. And what I'm going to do on this battery here is I'm going to reverse bias this. So what that means is we're going to put the positive on the N, and this is going to be our gate lead. Well, what's going to happen, the reaction, and we know what happens in a diode junction when we reverse bias a p-in junction. It creates what we call a depletion region. So what happens and how much depletion region you get depends on how much reverse voltage you apply. And that's what happens. So when I reverse bias a diode, the more reverse bias I put on it, the depletion region just gets bigger. And then it gets to the point where it breaks over. And this would be, so we would have a breakover voltage drain gate to source, that if we exceed, we're going to burn up the transistor. But what happens when I reverse bias this is it starts setting up a depletion region. Well, this depletion region is depleted of majority carriers. So there's no majority carriers within that to handle a current. So now what's going to happen is we're literally or physically or electrically, I should say, decreasing the size of the channel. Now, if we decrease the size of the channel, what happens? Well, the resistance of the channel goes up, which means your drain current will go down up until we get to a point where we cut it off. And that point would be where we spread this out. Now there is no channel between the drain and the source, and the transistor cuts it off. And this would be what we call the voltage gate to source cutoff. Okay. Now, a little different too that we need to understand is on an FET, your drain current is equal to your source current because we're not supplying a base current. So on a BJT, your collector current is slightly less than your emitter current because your emitter current is a combination of your collector current and your base current. But on a FET, the drain current and the source current are equal to each other. Another point we need to understand is the transistor is turned on as hard as it will actually turn when the gate to source voltage is equal to 0. When the gate to source voltage is equal to 0. So that's when the current in the JFET, the junction field effect transistor, will be maximum. When we start increasing that reverse bias voltage, then what happens? Well, the FET starts moving toward cutoff. When we hit the point where we completely close the channel up with our reverse bias voltage, then that is going to be the voltage gate to source cutoff voltage. And this is what this is demonstrating right here. And now what I have, if it works, I'm connected to one of our computers at the school through the internet. And I'm down in Mobile, so we'll see if this is going to work. Is that if I can find it, I might have to go back and load it up again. Oh, in fact, it's down here. Is that I've set up a FET circuit on one of our computers in our lab using a technique called VPN or virtual private network, which is really neat. And what we're going to do is we've got a voltage right here that we're going to be able to change. And what we're going to do is we're going to put several voltages up here on our gate, and we're going to do this with 2 batteries. So similar to our well, let's drop back just for a second to our slides. And I don't know where the open slide presentation's at, but let's go up in and actually look at the symbol. So this is I needed to show y'all this too. So this is basically what's going on. So the gate lead completely surrounds the channel. Now I've drawn it here as a circle, but it could have just as well be done as a square. So this P on this side is connected to that P on that side, and this would be an N channel. Now if this was a P channel FET, JFET, then what we would do is we'd have the same thing, but the gate actually surrounds the channel. Okay. And let's go on down to the symbols. So what we have and what we need to know, it's just like on a bipolar junction transistor. On a bipolar junction transistor, let me get back down to the symbols. And when we draw the symbol for a bipolar junction transistor, the arrow points toward the end. So the arrow is pointing toward the end. Well, if the arrow points toward the end, then this would be an NPN transistor. Well, if I come over and draw this, the arrow points toward the end. So this would be, the end would be right here. So that means this would be the symbol for a PNP transistor. Well, this is the same thing true for the JFETs, except now if the arrow is pointing in, pointing toward the channel, so this is representing the channel right here. If the arrow is pointing toward the channel, then this is a symbol for what we call an N-channel JFET. If the arrow points away from the channel, then this is going to be, that means this guy here has to be a P-channel JFET. And there's our two symbols. Now these are our symbols, so the gate is the one that's actually connected to the arrow. So this is a lot different. So on a bipolar transistor, the arrow was the emitter. Well, in a JFET, the arrow is the gate. So that's a big difference that we need to learn. And then normally we'll put the drain up, but that's not exactly right. And the other gates would be the source. And you can literally take an ohm meter and put it across this, and no matter which direction you hook it up, it's going to measure the same resistance. Because that's all it is a channel made out of N material or a channel made out of T material. Now, if I came over here and put my ohm meter on the diode scale, then if I put my black lead here, so you got to remember, so let's go back and look at the N channel real quick. So the N channel, at the gate is actually P. So the gate would be P, and then the channel would be N. So if I was going to check that with an ohm meter, then if I was going to check that junction, then this is the P, and the channel is the N. So what we would do is we'd put our plus here, and we'd put our minus there. And what we should do is read approximately 7/10 of a volt, because as far as I know, I've never seen these made out of germanium. All I've seen are made out of silicon. And then I should be able to change my polarity, and then I should read whatever your meter reads when it sees a reverse bias junction. And then we could do the same thing here. So we can check these guys out. So if I put an ohm meter across my drain and the source, I should get a resistance reading. And if I swap them around, I should get the same reading. If I reverse bias the gate to source or the gate to drain, it's going to read like a reverse bias, whatever your meter reads for a reverse bias P junction. Most of your neuter meters shows OL for overload. When we forward bias the gate to source, and you need to check both of them, by the way, because you might have a defect right in here. So what you would do is you'd come up here and you would still check both sides with your meter. So you'd take a reading from gate to source, and then of course from gate to drain. And if you flip the meter around, you should read infinity. So what we're doing here is what we're doing here on our electronic workbench is that we're looking at an N-channel FET. Now what we're going to do is if we're looking at source current, I could have put the ammeter up here in the drain. It would have been exactly the same thing. And to measure the drain current or the source current, but usually we say the drain current. So kind of like when on the BJT we use the term collector current all the time, even though the emitter current would be just as good to use because they're basically the same. So what we're going to do is over on this power supply right here is we'll start off with it at minimum voltage. So what we're going to do is we're going to start off with 0 volts. And what we'll do is we'll make this supply equal to 5 volts. And what we're going to do is we're going to come out here and turn on the simulation, if I can find it. Let me pause this and see if I can get up there to the switch. So I'm going to come up here and unpause it and then move back over to my transistor. So you can see right now we have a 0 on our gate to source. So there's our 0. And then up here we have 5 ohms. And right now we have 250 microamps. And we'll go ahead and boot this up to 10 volts. Okay, turn our simulation, then turn off. So we still got 250 microamps, and we'll explain that later on. So notice right now when I change this, the source current doesn't change. So what happens when I increase the size of this resistor right there? Increase the size of this supply. So notice this is an N, right? You understand? So this is a P. So we're going to reverse bias this. So we're putting the negative toward the P and the positive toward the N. So this should cause, when I start reverse biasing, it should decrease the size of the channel, and we should expect the collector current, the source current or the drain current to go down. So let's go ahead and double click on this, and we'll just make this 1 volt. Okay. Turn the simulation back on and look at this. So what happened? The drain current went down. Isn't that interesting? But look at your base current. What's your base current? Your base current is 0. And why is it 0? Because it's a reverse bias junction. So what we're doing is we're controlling this current with an electrostatic field. So let's go ahead and raise this up to 2 volts. Okay. Turn the simulation back on. And look, now the gate current, now the drain current is 0. So what we've now done is we've exceeded the gate to source cutoff voltage. So let's go ahead and we'll reduce this down a little bit. Let's go down to like 1.5. Okay, we'll turn the simulation back on. And what you notice now, we have a gate. So 1.5 volts is below the cutoff voltage. Now let's see if we can go up this in incremental. So this is 1.6. Okay, and now it's down to 14.29 microamps. Okay, let's go up to 1.7 and turn our simulation on. And now it's down to 8.25 or 8.3 microamps. So notice, the more reverse bias voltage we put, the actual drain current, source current, actually goes down. So we can come up here and make this 1.8, and we'll see where our cutoff voltage actually is at. Turn this back on. And we're down to 3.77. But look at the current right here on our gate. We have 0 current because this is a reverse bias junction. But what happens is the more voltage we put here, the more we increase the depletion region. As we increase the depletion region, the size of the channel goes down. If the size of the channel goes down, then the drain current or source current goes down. So it looks like this guy here, let's see if we get any current at 1.9. And we'll see exactly where this guy actually cuts off. So we still have, so it looks like 1.2 is the magic number. So, but notice as I keep increasing my voltage gate to source, then the current flow between my source and my drain keeps going down. So we'll go back up to 2. So it looks like 2 volts is pretty close to the cutoff voltage for this bipolar transistor. For this JFET. And when we turn it back on, we have 0 current. Okay, so right now we are in cutoff. Another thing I want to show y'all is, well, we can refer to this as the pinch-off voltage. The pinch-off voltage is once you get up to a certain voltage, the collector voltage can change. The drain voltage can change, but the current flow through the FET stays constant. And that's what I demonstrated a while ago. So let's turn it back on. Let's come up here and put some voltage on here. And let's drop it back down to 1 volt. So what I'm going to do is I'm going to come over here and change this voltage right here. So let's drop it down. Now, first of all, let's note the current flow. Well, the current flow right now is about 77 microamps. And what I'm going to do is I'm going to come up here and change this to 5 volts. Now, most people would say, okay, if I lower the voltage, the current is going to go down. but that's not true. As long as we're above a voltage that we refer to as the pinch-off voltage, the current flow through the FET is going to be constant. And so it's not like a BJT so what happens is it's going to allow us to allow this voltage right here to change. But if I don't change this voltage right here, the current flow is going to stay the same. So what happens, even though your drain current, your drain voltage is changing, even though your drain current is changing, you're still controlling the current flow with your voltage gauge source. So let's see when we lose this control. So let's start lowering this down again. So let's go down to 3 volts. Okay, and let's turn this in. So it's still the same. Let's drop down to 2 volts. Okay, still the same. Let's drop down to 1 volt. Okay, so it dropped. So what we just got into is we got below what they call the pinch-off voltage. So the gate to source pinch-off voltage, this is the voltage where if you get above the pinch-off voltage, your voltage drain to source can change without changing the current flow through the So above the pinch-off voltage, if you're operating above the pinch-off voltage, then your current flow is controlled by the gate voltage, and it's controlled precisely. And you know, when we did the bipolar junction transistors, when we did what we call the collector characteristic curves, those guys varied with a slant. These guys are almost parallel with the y-axis or the x-axis. I get those confused all the time, which is really, really neat. So above pinch-off voltage, you're controlling this with this gate to source voltage. Below the pinch-off voltage. So what we're going to do to operate this guy as Class A or in linear mode or whatever is we're going to make sure that we operate this thing with a voltage drain to source that's above the what we call the pinch-off voltage. And where do we find this information at? Well, we find it in the data sheets for the FET. And we're going to look at it. I think we're using a 2N5857. Unfortunately, I didn't bring my lab book. And also, I didn't bring my textbook with me. So hopefully you're using your textbook to look this up. But I don't think this right here. But what's really neat is we're using an electronic workbench to literally come in and watch what the pinch-off voltage is. And also, we know what the cutoff voltage is now. So the cutoff voltage is when we put a voltage gate to source that literally cuts off the channel. The pinch-off voltage is the voltage where the drain voltage does not control the current flow anymore. What controls the current flow is the voltage gate source, which is pretty neat. Now, if we were going to do this with a P channel, then what we would do is we would flip these batteries around. So on a P channel, we would control it with a positive voltage gate to source. With an N channel, we're controlling it with a negative voltage gate to source. So what you're doing is you're controlling it with the same polarity as a channel. If you just remember that, we control it with the same polarity as a channel. Or if you remember that this is the P and this is the N, and we want to, this is the N, this is the P, and what do we want to do? We want to reverse bias this thing. Okay, so let's go back to our PowerPoint, which would be, where am I at? This guy right here. Okay. So this is what they're showing us here. The demonstration that I made, I think, was a lot better. Here they're actually showing the size of the channel change. But when we actually put an ammeter up to it that we could see instead of using these static ammeters and these static voltmeters, hopefully you saw the dynamics of these things. And another thing I wanted you to realize is that no matter what voltage we put, as long as we were below the breakover voltage, there was no current flow that we could measure. No current flow that we can measure. No gate current. Absolutely no gate current. Isn't that neat? So what we're doing is we're using this reverse bias voltage to control that, to control the size of the channel which is going to control the current drain source. All FETs have a very high input resistance, and this is really good, especially when we start dealing with sensors and stuff like that. Touch screens. So if I'm going to come up and hit a little touch screen, I have a high internal resistance, and I want to come up and touch something that has an extremely high input resistance, so it doesn't load my signals. So a lot of your touch screens use FETs. With the field, maybe not a JFET, but some form of FETs that we're going to look at anymore. So JFETs have a high input impedance due to the fact that the PN junction is always reverse biased. So basically, a JFET will not load a source. And so the source thinks it's running into an open circuit. If the P channel is constructed of the N material and the two P regions are connected to the gate, during normal operation, the JFET is normally operated. I should take out normally. During normal operation, the JFET is operated with the gate to source PN junction reverse bias. If we forward bias, it's going to act like a diode, and we lose total control of the transistor. Now, why we put normally, and I think I explained this to you before, is why we put normally is that engineers, if they've got something that operates that won't burn something up, they will figure out a use for this. But during normal operation, the JFET the gate to source is reversed bias. And don't that sound like a very good test question? The reverse bias on the gate to source junction creates a depletion region along the PN junction and restricts the channel width. We refer to this as depletion mode. So a JFET is a depletion mode FET. Depletion mode FET. So if your gate to source voltage makes the channel smaller, then it is what we refer to as a depletion mode FET. And we have two categories. We have JFETs, which we're talking about now, and MOSFETs or IGFETs. So what I'm saying if the gate to source voltage, no matter what type of JFET that we have, decreases the size of the channel, this is referred to as depletion mode. All JFETs are depletion mode FETs. That sounds like a good test question too. So this is what we just demonstrated. So we're coming up, this is cutoff voltage right here. We saw that. So that's when our gate to source voltage gets so big that it basically closes the channel up. Then when we start coming up here and we get up above pinch off voltage, so here's our voltage drain, here's our drain voltage right here. So once we get above that, my drain voltage can change, but my current doesn't change. So once we get above pinch-off voltage, the FET is being controlled by the gate to source voltage. If I don't change the gate to source voltage, so we're here using 0. Now this pinch-off voltage is referred to as IDSSS. So we need to operate it above IDSSS in the data sheets to allow the gate to have total control over the current. Now what we do is we come up here and we develop these, and this will show you what actually happens. So here this would be IDSS, right? You understand? And then this would be where we would operate. So IDSS is given at we call this operating above pinch off. Are we okay? The channel width and the resistance can be controlled by varying the gate voltage. Pinch-off voltage is voltage where IDS becomes constant. Cutoff voltage is the voltage from gate to source that causes the drain current to reach approximately 0. Of course, it doesn't go to 0, but in our simulation, the meters that we had on our simulation couldn't measure. And so this would be the cutoff voltage that we demonstrated. We looked at this already, set this up. A JFET, now the problem is when we have gain on a JFET, So a JFET we're using, so the gain, let's see if this is on the next slide before I get too far. Okay. The gain of a JFET, the gain of a bipolar transistor, we refer to this as beta, or also referred to as H of FE. Okay, H of FE. And this is equal to IC divided by IB. Well, the problem is on a JFET, we're not using an input current. We're using an input voltage. So the gain of a JFET is going to be equal to ID divided by voltage gate source. Now think about this a little bit. Strangely enough, if we remember Ohm's law, R is equal to V over I. And my answer is in units called ohms. Here, ohm should be given in uppercase letters because that's the name of a person. So we look at this gain is ID, so we have an I over V. That's opposite of that right there. And we call this, by the way, it's given in data sheets as GFS, and we'll look at data sheets later on in the lecture. And it's called the forward transfer conductance ratio. I'm running out of room. Sorry. And the unit is the mho, which is ohm spelled backwards. Mho is in lowercase letters. So I guess they came up with this because it's opposite of an ohm. So it's the inverse of an ohm. So this is the way they specify the gain of and it's usually in micromodes, by the way. And when we get to the data sheets, I'm going to cut off the lecture right now, and I'll finish card. So we're going to do this in multiple parts, which will make it easier for y'all. So when you look at the lecture if you can look at this part of the lecture on Thursday, and then pick up the rest of the lecture. You know, our class goes for a long time, so pick up the rest of the lecture probably during the week. I don't know how many parts I'm going to do on this right now. It might be 2, it might be 3, but instead of trying to do one big old long 3-hour lecture, what I'm going to try to do is limit my lectures to around 30 minutes, and then spread it out over time, because literally y'all got the whole week, and I know it gets kind of boring sitting in front of a computer listening to a lecture with a set of headphones in your ear. And this will be a lot better for us to work this out. So I'm gonna go ahead and cut this off right now and go ahead and upload it and get it up on Blackboard tonight before I turn it in, and I'll finish the lecture tomorrow night, or I'll work on the lecture. But still, even if I try to do the whole thing tomorrow night, what I'm going to do is try to split it up into 30-minute whacks. So y'all have a blessed night, and I hope y'all have a great Thanksgiving, and I'll finish up this lecture tonight. I mean, not tonight, tomorrow night.